So hello everyone, this is lecture 24 for the classical physics. In the last lecture we were discussing some question regarding the Lagrangian. So let's see one more question. Here is your question. A particle of mass m is constrained to move on a surface of a cylinder of radius a. It is subjected to an attractive force directed towards the origin and is proportional to the distance of the particle from the origin. So we need to write the Lagrangian in the cylindrical coordinate, then obtain the equation of motion, so that angular momentum along the z-axis is constant of motion. Then we need to prove that motion of the particle is simple harmonic along the z direction. So let's see the question. The figure will be something like this. A particle is bound to move on the cylindrical surface, and we need to write the Lagrangian in the cylindrical coordinates. So, and force is given is directly towards the center, so it is a kind of example of central force. So we can write this force as F equal to minus kr, because it's towards the center, and our radial component is going this side, so that's why I write it here minus. Now if you need to find the potential energy, so what it will be? It will be minus F dr. So F is this kr, it will give you kr square by 2, simple integration. Now see this r, and this is cylindrical coordinate system, so this will be s, this distance is z, and this phi will be what? This phi will be from here, means when you take the projection here, so this will be your phi. So that's how you can find the coordinates. Now in place of r square, you can write s square plus z square, because this is a right angle triangle, so r square will be s square plus z square. So in place of r square, I written this. Now this distance or the radius of the cylinder is given as r, so we can write in place of s equal to r. So this will turn out to be this, u will be 1 upon 2k r square plus z square. And Lagrangian is what? Kinetic energy minus potential energy. So kinetic energy for cylindrical coordinates, we know this expression, s dot square plus s square phi dot square plus z dot square, minus potential energy is this, so I have written this. Now see, this s is not changing, it will remain same, because we know the cylinder is of fixed radius capital R, so s dot will be 0, so this component becomes 0, so only this component will be remaining, and in place of s square we can write r square. So this will reduce to this form, half s square phi dot square plus z dot square plus minus half k r square plus z square. Now see, this is Lagrangian, so we have already solved for the Lagrangian in the cylindrical coordinates. Now we need to check for the angular momentum, constant of motion. So how you can check? See, this equation is cyclic coordinate, means what is the cyclic coordinate in this equation? Is phi. So because you have phi dot but there is no phi, so that is your cyclic coordinate. So p phi will be del L by del phi dot, and it will give you mr square phi dot. In place of s you will get r, so it will be ms square phi dot, and this is constant of motion. Now we need to do the third part, or the last part. We need to prove the motion along the z direction is simple harmonic. So let's see. First we need to write the Lagrangian equation of motion. So how you can write along the z direction? So it will be dy dt of del L by del z dot. So find it from here. So you will get mz double dot, and del L by del z will be minus kz from that equation. Now Lagrangian equation will be this subtracted from this, so mz double dot minus kz, so it will give you m you will take the common, so it will give you z double dot plus ky mz equal to 0. Now see, this is the equation of a simple harmonic oscillator, differential equation, so you can compare this term with the omega square. So this is your frequency, and this equation shows that the particle is moving with a simple harmonic motion along the z direction. So that's how you can prove this. So today we will understand a new topic, that is generalized force. So I already told you what are generalized coordinates, and then we came to the generalized velocity, and generalized velocity gives you generalized momentum. Now change in the generalized momentum gives you generalized force. So that's how it came. So there are many proofs of generalized force, but I will give you the straight one, very easy one. So you know, the work done will be remain same whether it is done in the Newtonian mechanics or in the Lagrangian mechanics, so it will remain same. So let's find the work done in the Newtonian mechanics. So here f dot dr, it will give you work done, so I can go from 1 to 3 x y z, so total work done will be fi del xi, and it will be means f1 means fx Fy and Fz. So this will be your total work done in the Newtonian mechanics along the all three directions. But if we find this same expression for the generalized coordinates, so it will be Qj del Qj, and means this is your generalized force. So we need to find the expression for this. So this will be your work done in the generalized coordinate system or the Lagrangian coordinate system. Now this work done and this work done will remain same. So we'll equate these two. Now here find the partial derivative with respect to Qj. So you will get Qj here because all the terms will be 0, only this j term will be remaining, capital Qj. And here they will remain same and all will be differentiated with respect to Qj, because here you will getting all the terms which have the coordinates these Qj and all. Okay, so means every possible coordinates will be having this Qj. So this derivative will give you your generalized force. Okay, so here it is just this Newtonian mechanics, and here these variables can be written in the form of generalized coordinates. That's why we are finding this derivative. So they can give you the generalized force. So it is the sum of all the components in the real space. Okay, so first you need to find the coordinates of these in the terms of generalized coordinates. Then you will write here. Then you will differentiate with respect to Qj. That will give you generalized force. So this will be your standard expression for the generalized force in the coordinate system of generalized coordinate system. So there is every capital Qi generalized force associated with the generalized coordinate q1, small q1, and that is given by this. Means here you will have this 1 and this will be Fi del xi, as I already told you. This is force is along the q1 coordinate. Okay, so you will differentiate all the terms with respect to q1 to get the force along the 1. Okay, so it will be 1 here, and here it will be x del x 1, and here also 1, here also 1, but here they will change to the xyz. Now there can be force in terms of q1 coordinates or the q2 coordinates and q3 coordinates. All the generalized coordinates can give you force fx, and the same these del x del y del z, and then you will differentiate them with respect to q1 and they will give you the force along the q1. So I hope you understand this point. Now we will understand the conservative system and non-conservative system in the Lagrangian mechanics. So what are the conservative system? You all know that involves the conservative forces, means the mechanical energy should remain constant, and only conservative systems involve the potential energy, because here we can write force equal to delta V. Okay, how you know this expression? Means you know if force is conservative, then del dot F will give you 0 definitely. Then you can write this force as gradient of some scalar component del phi, and means del dot del will be 0. So that's how you can write del dot F equal to 0, and this F will be nothing but del phi, and where phi is some scalar potential. So that's how you can write means only potential energy involved in the conservative systems. There is no definite potential energy in the non-conservative systems. So most of the time in the conservative systems you will find potential as a function of x, y, z and t. Means they will not be function of velocity or all, they will be just distances and time. And in the generalized coordinate system we represent this potential by qt, so it will be in the form of this, and in Newtonian mechanics it will be in this form. So there won't be any q dot term or x dot term in general. So qj, we find this expression is this fx del x by del qj. Now see, this fx is nothing but del v by del x. I just told you it is gradient of potential. So now this will cancel out and it will give you del v by del qj. So generalized force can also be given by this expression. So this is a more simple expression, because now we need to only find the potential in terms of generalized coordinates and just take the derivative, it will give you force. Now see, in the generalized, when force is conservative, then Lagrangian is given by this expression, del qj dot minus del by del qj equal to 0. Now Lagrangian is nothing but t minus v, so we will expand it along the L will be t minus v, so it will be del t by del qj and del v by del qj and minus, so we will get this expression. Means when you will get minus del v by del qj dot, so v is not a function of qj dot, so that will give you 0. So but this will give you del t over del qj and del v over del qj. So when you expand all these terms, 4 terms, so you will get only one term 0, that will be del v over del qj dot. So in the right hand side we will get this, and the left hand side we will get this. Okay, so it is t minus v, So t minus v, t terms will remain, v will give you 0, and t minus v, t will remain, and v will go that side, and it will give you this minus expression. Now this expression is nothing but capital Qj, this is your generalized force. So this expression gives you, means now from here you can find the generalized force, from the kinetic energy you can find. So this is the case when the force is conservative, or this is the case in general when there is force, means there is a potential which is not a function of velocity. Now there are some very rare examples where the potential can also be a function of velocity. Okay, so how then this force will be defined? So it can be, means potential can be a function of velocity also. So then how you will find this, what will be your generalized force? So let me give you an example of this type of thing where you have the potential function of velocity. So a charged particle propagates through EM fields. So when you study the electromagnetic theory, I will teach you, then you will see this equation for potential where it is q phi minus, means potential energy is given by q phi minus q v dot a. So this a is nothing but vector potential, and this is your scalar potential, and v is your velocity. So there you will find this potential energy depending on the velocity. Now from this expression you can just see that now the term we are making 0 here, del v over del qj dot, will not be 0 now. Then you will expand and you will get 4 terms. So you will get 2 terms here and 2 terms here. So this term and something more. So that will be this term, d by dt del v over del qj dot, because we made this 0, but now it is depending on velocity also. So this won't be 0 now. So you will get this expression, and now this will be your generalized force, more expanded form of generalized force. First we defined only this as force when this is the function of only positions and time, but now it is a function of velocity also. So complete generalized force will be this, and this is your cause and this is your consequence. Okay, cause and consequence, remember this. So now this is your generalized force, more expanded form. Now it is a more generalized form. How? When this potential is not a function of qj dot, then this force will reduce to only this, and we get this expression which we derive for this. So this is a more generalized expression for the generalized force. Qj will be this. So remember this expression. Now for the non-conservative systems, those mechanical system which has, means what is non-conservative system, it will include some non-conservative forces also. So it can be sum of non-conservative and conservative forces. So those mechanical system which has at least one non-conservative force is called non-conservative system. May have both conservative and non-conservative forces, so at least one will be non-conservative. So for the conservative ones you will get this qj, and for non-conservative ones you will get this qj dash. Okay, so this will be your forces, and they will be equal to this. Now for this qj you have this expression, and qj dash will be this. So you know how this get this, we just derived this. So now this expression will go this side, and it will again give you Lagrangian when you will get t minus v, t minus v from them. So this expression will be like this. Now what this proves? This proves that for conservative systems we know what we have here, 0 in the right hand side, but for the non-conservative systems we are having some non-zero term. So this is the difference. For the non-conservative and conservative system you will get something here for the non-conservative forces. Now let's summarize this. Mechanical system has two type of things, conservative system and non-conservative system. For conservative system you will have Lagrangian equation of motion will be equal to 0, and for non-conservative you will have something value here. Now this if it is conservative and it is then generalized force will be given by this, and if potential is only function of position and not the velocity, then this will reduce to only this. So this component will be 0 and generalized force will be this. Now this can be reduced to this form also, and this is your generalized force. Okay, so I already proved these results. Just remember these results, very important going to the exam point of view. So let's take an example. Write the Lagrangian for a charged particle traveling through the EM field. So if charged particle is traveling through the EM field, then it will have velocity component also in the potential. So Lagrangian is given by half m velocity square, so velocity will be vx square plus vy vz, so x dot y dot z dot. Now potential is q phi, the scalar potential and the vector potential, and from here you will know in the electromagnetic theory E will be minus del phi minus del a by del t, and B is nothing but del cross A. Okay, so you just substitute these values here. Means here if V is in terms of Vx, Vy, Vz, then A will be Ax, Ay, Az, so you will get what? Vx Ax, means this expression will reduce to this form. Vx will be x dot, so x dot Ax plus y dot Ay plus z dot Az, Q, and this form. Now see, we need to find the, if we need to find the momentum, then Px will be, means now we have Lagrangian, we already find this. Now if you need to find the momentum along any component, so Px will be del L by del x dot. So it will given by 2, then it will give you mx dot here, and here also x dot you have here, so it will give you qax. So you will get two components in the momentum also. So this, let's differentiate them. So this is nothing but momentum carried by the particle by traveling, and this is momentum associated with the EM field. Okay, so remember this thing. Now the last topic for today is what happens in the relativistic case to this Lagrangian. So we need to write a Lagrangian for a relativistic free particle, or just not need to write here free particle, we can just find for any relativistic particle. So Px momentum in the relativistic particle, how it is given, mv. So m is nothing but m naught by under root 1 minus v square by c square. So you can study this relativity in the STR. I have given in the complete playlist for STR, special theory of relativity. So that is also part of classical physics, so you must study that also. So momentum is given by this, so mvx. So m is nothing but this is your rest mass, and v is nothing but vx square plus vy square plus vz square. Now this px is nothing but what, del L by del x dot, and x dot is v. So we can write this px as del L by del vx. So this is equal to this again. Now see, we need to find a Lagrangian, so we will solve this differential equation. So del L will be, take this del vx to this side. Now we will integrate to get the Lagrangian. Now in the denominator you have v is nothing but vx square plus vy square plus vz square divided by c square. Now this will give you L here. Now we need to integrate this also. So we will assume this complete denominator term as eta. Okay, so 1 minus v square by c square, v is this complete term, so v square by c square is eta. So if you take this eta, then you will find the derivative with respect to vx, so it will give you minus 2 vx by c square. So from here del vx will be equal to c square by 2 del eta. Okay, so this term is equal to this. So in place of vx delta vx, we can write minus c square by 2 del eta, and this is all complete is eta. So you will get this form. Now you can integrate this thing. It is nothing but eta minus 1 by 2 plus 1 divided by minus 1 by 2 plus 1. So it will give you this. 2 will cancel out, and in the denominator you will have eta, and you will have some constant after integration. This is constant of integration. So now you have Lagrangian, but still you don't have this value of c1, that is constant. So how you can find this? Now we will take the help of non-relativistic case to find this c1. How? First write this Lagrangian in this form, means in place of eta we can write 1 minus v square by c square. So this is your Lagrangian, but c1 is variable, means you don't know c1, so you need to find this constant. So you know, we can write this expression by expanding binomial theorem. 1 minus v square by c square 1 by 2 will give you 1 minus 1 by 2 v square by c square. So you can write that expression in this form also, and here it will give you minus m naught c square and minus plus half m naught v square by 2 plus c1. So this is the case in the relativistic case, but when it is non-relativistic case, then this term won't come in the expression, because this is your relativistic term, and the means rest mass energy is not included in the non-relativistic regime. So you have a Lagrangian of this form in the non-relativistic regime. This is a Lagrangian in the non-relativistic regime, and in this regime also, means when we find this equation, in this also this is not relevant. So if the case is non-relativistic, then if you ignore this term, then this term will be equal to this term, because this is the case in the non-relativistic regime. So this will be equal to this. From here you can compare the c1 is nothing but minus vx. So L equal to half mv square minus vx. In place of c1 we will write vx, and you will get your expression. Now this is in the case of non-relativistic regime, but now we have this expression L equal to this. In place of c1 we will write just minus vx. So this is your Lagrangian in the relativistic case for a free particle. You will write this, not free particle, just any particle, because for the free particle we have to take the potential 0 or any constant value. So you can find this, means potential function of x, So this will be your Lagrangian for a relativistic particle. So that's it for today. We will discuss some more questions and we will practice more. Then we will go to the Hamiltonian. So that is for today. Thank you everyone.